let's quickly move on to the second session about regression. We will see how to use decision tree, random forest, and KNN model to solve regression problems. We have seen how to use them to do classification problems. Now let's see how to do regression problems. So in this small session, we will use a new data set called Boston. It is built in the mass package. So it contains some information about house values in the Boston area. Each unit is a small district or neighborhood. So the response variable is median house value. Let's see. We have a bunch of feature variables. So this slide shows you the descriptions of different variables. Okay? The response variable is median value of owner-occupied homes in $1,000. So the unit is $1,000. Okay? And there are a bunch of variables. For example, this crime function variable is per capita crime rate by town. Yeah. And the second is proportion of residential land zoned for lots over 25,000 square feet, etc. Okay. A bunch of variables, 13 of them. Okay. So it's perfect for a regression example. So now let's consider let's split the data first, right? Because essentially we want to evaluate the performance of those machine learning models on the test set, right? For out of sample predictions. So we split the data into a training and a test set, right? And then let's fit a multiple linear regression model first as a reference line or baseline, right? So we just throw all of the variables into the model, right? Using the training set only. So see that actually most of the variables are quite significant, okay? Actually, so it is a very good data set for regression. You can see high R-square values, which is usually like a happy result, okay? Not a very miserable result. So the R-square is 0.7262 and adjusted R-square is 0.7171. Okay? So notice that it is a full model and it is a very simple model. We didn't do anything, right? No data transformation, no square term or interaction. It's just a plain multinomial model. Right? The adjusted R-square, the R-square is 0.7262. Right? So we can assess the model using the test set. Okay? So first, let's see the in-sample prediction. We can predict the Y values, call it Y hat train for the training set. And then we can calculate the R-square by ourselves. Okay? It's actually equal to the correlation between Y and Y hat. Okay? So this is a new way to understand the R-square metric for regression. Okay? It is actually the correlation between Y and Y hat. Okay? And if you square it, you get the R-square. So for example, you can compare this value with this 0.7262, right? So exactly it's correct, right? The correlation. And because of this, we can also calculate out of sample R-square for our test data set. So we first do prediction that Y hat and calculate the correlation between Y and Y hat for the test set and calculate R-square. And it turns out that the R-square is even higher than the R-square in the training set. It's very interesting, interesting phenomenon. Usually it should be smaller than this one. Right? And if you have had other classes about regression, you might doubt the result, you would say, okay, R-square is not a very good measure for regression models, for multiple regression models, because by adding more terms to a model, R-square can only increase, right? That is true, but that is true if we don't split the data. Okay? If we split the data, then R-square is still a good metric to be used to compare different models for the performance test set. For example, so this is kind of like our reference line, right? For the performance on the test set. Right? This is a multiple regression R-square. Right? We are not comparing it with other models with fewer predictors using the test set. We are comparing this R-square with other models. Okay? We calculate the out of sample R-square for different models and see which one has a higher R-square. Okay? So we have no concern about this anymore. Okay? So because we're not comparing the full model with models with fewer terms. Okay? All right, now let's take a look at regression tree first. Okay? Still, we can use the rpart function. Right? We can create a decision tree using rpart. We can also create a regression tree using rpart, the same function, same package. Right? And even the arguments are similar. I specify the formula and the data set and the method. Okay? The method determines it is a classification tree or a regression tree. Okay? If method equals class, then it's a classification tree. If you say method equals ANOVA, it is a regression tree. Right? So usually the model can determine. Okay, you don't have to specify this, I think, but it can determine which model is needed. And lastly, the control equals. So this one can be used to tune hyperparameters, change hyperparameter values. For decision tree, of course, we have different hyperparameters. For example, mean split equals 30. If you set this is the minimum number of observations in the node before attempting a split. So this can be used to control the size of the tree. And also CP, the complexity parameter. We have seen this before. So it will do a split only if it will decrease the overall lack of fit by a factor of 0.001, for example. So this last term can be used to control the size of the tree. So now let's fit a regression tree using our model. We just use the full formula. So median value to the period and specify the training set and method equals ANOVA and control. We use these two hyperparameter values. Oh, actually I use 0.01 instead of 0.001. Right? So I believe this is the default value for CP. Right? And then we can plot the tree. Okay, so it looks like this. So it's very similar to a decision tree, how a decision tree looks, except that the values in each label is kind of different. For example, let's consider this leaf. How about let's consider this leaf? Okay, so this 20. What is this 20? This is a mean value of median housing value of all of the observations in this node. Okay, and of course this 82 is still the percentage of observations in this subset. So you see 82% plus 18% is 100%. Okay, so 82% of observations are in this node, in this subset. And if we take the mean value of all of the response values, so that would be this label of 20. So that's the only difference. So you can see that the leaves are ordered from smallest to largest, um, according to the labels on it. And the darker the color, the higher the mean value, average mean value. And also we have percentages. And similarly, I think that the number of rooms and this LS LStat, and also, yeah, only a few variables are used to construct this tree. Actually, only 4 variables are used. All right, now let's see how to tune the CP parameter using caret. So we previously used the caret package to tune the hyperparameters for the random forest. Okay. So now let's use it to tune a regression tree. So load the package and then set the seed and then specify the cross-validation coefficients. So we use repeated cross-validation, 3 repeats, and tenfold cross-validation. Right? Because our data set is, I don't remember, it's not very big, so it's okay, I think. Right? And then specify the grade. We consider all the values between 0 and 0.01. Right? And the jump is 0.002. So essentially 6 values, right, from 0 to 0.01. And then train the model. We use root mean square error as the metric. The smaller, the better. And so this is the result. Right? If you compare the root mean square error, you see root mean square error is minimized when CP is equal to 0.002. And it's also put here. Right? So this is how we tune a decision tree using the caret package. And what is root mean square error? It is equal to square root of the mean square error. Okay, mean square error is just defined in this way. So this is definition of the mean square error in machine learning. It's not a definition of mean square error in statistics. The difference is the denominator. In statistics, we use this denominator, where P is the number of predictors in your model. If you do this, it is an unbiased estimator of the variance of the error term. But in machine learning, we really don't care about estimating sigma square. So we only care about the overall noise or error in your model fitting. So that's why the root mean square error is defined this way. And another way to evaluate regression models is to use R-square. As I said, you can calculate R-square by calculating the correlation between white and white hat first and square it. Okay. So let's compare the performance of the models on the training set and test set. Right? So we first created 2 functions to avoid repetitions in future code. So we basically summarize the result here. The root mean square error on the training set and test set, and the R-squares are actually the same, right? So which is very interesting. Okay. And then let's move on to random forest. Right? Random forest can also be used to solve regression problems because, a random forest is just a collection of bootstrap decision trees. So naturally, if a decision tree can be used for regression models and be used as a regression model, then a random forest can also do so, right? So let's see how to do it. Still, we use the random forest function in the random forest package. Okay. And we just use the full formula, specify the data set and the number of trees. Okay. So this is we just use the default options for other hyperparameters. Right? So we only specify the number of trees in the random forest. So by default, M try for regression model is P is equal to P. P is the number of feature variables in the formula. So this is default behavior. Okay. And we fit the first tree and calculate the R-square and root mean square error for the test set. Okay. It's very high. It's 90.2%. Although there is a difference between the training set R-square and the test R-square, but in general, the R-square on the test set is much higher, and it's much higher than the decision tree. The decision tree is 84.7%. So now we have over 90% without tuning. This is the raw version of random forest, right? And of course, we can also use cross-validation to tune a random forest. Just pay attention, random forests involve a lot of trees. Okay, usually there are a lot of trees. So if we use cross-validation, don't use a big number of fold, and don't use a big number for this number of repeat. If you use repeated CV. So we would just use a 5-fold cross-validation with run one round. Specify the possible values for M try. Want to tune M try. We consider odd numbers between 1 and 13 inclusive, and then train the model. Method is RF. So let's see the result. It turns out that if we use root mean square error, so matrix is root mean square error. So you see the root mean square error is minimized when M try equals 5. So this is essentially, so this is the optimal one. It was the smallest root mean square error. At the same time, you see that when M try is equal to 5, the R squared is the maximum. It's the biggest. So they are closely related, actually. Alternatively, we can just directly use the tune RF function. So this function is building random forest, the random forest package. So we can tune using this. We can use this to tune and try as well. And of course, this method is kind of restricted because the values for M try can only be a factor of some base step, the start value. For example, if we let M try start equals 2 and step factor equals 2, then it will only consider 1, 2, 4, 8, 16, etc. And the program will stop if it stopped improve. Which means it will stay. It is stabilized, at some local optimum. Right. So if we use this method, we see that the OOB out of bag error is minimized when M try is 4. It's similar to the previous one. We got 5 because when we used the carrot package with cross-validation, we only considered odd numbers. And this one only considered even numbers. So there is a small discrepancy. It's not that important. And tune RF, remember, it does not use cross-validation. It only uses out-of-bag prediction error. Right? So it's kind of faster. Then let's refit the optimal random forest model. Let's let M try equals 5 and then do prediction and calculate R squared. It turns out that is equal to the first random forest model, and that of the first one, which means probably the first model also automatically choose a very good M try value. Although in theory, for the first model, M try should be equal to 13, which is the total number of predictors in the formula. But turns out that the result is the same. It's the same. And random forest can help us to figure out the importance of variables. So again, you can use the importance function to extract the importance metric. For regression models, the importance metric is increase in node purity. Increase node purity. For a decision tree, it was mean decrease in G, right? So now it's increase in node purity. I don't know exactly how this one is calculated. I think it's related to mean square error. So the decrease in root mean square error somehow. Yeah, the decrease in the overall mean square error or weighted average of mean square error. All right, so the most important variable is LStat. So this can be seen from the first decision tree we built, right? It's very clear. See the tree again. You see LStat is used multiple times. And also room number is also very important. And we can also see it in the list. Room number is the second most important variable. All right. Now let's move on to the last traditional machine learning model, and KNN, K nearest neighbors. So in the classification part, we talked about the KNN model, the KNN function, but that function, KNN, is built in a package called class, right? That package is for classification problems only. Now we are dealing with a regression problem. So we actually will use a different package called FNN. And within it, there is a function called KNN.reg. So this is only for regression problems. And before we fit the model, we need to prepare our data. That is because in the KNN model, we need to calculate the distance between any two points. And the distance, in order to calculate distance, all of the variables have to be numeric. We have to convert the variables. And also, it's better to scale the data, right? Because the distance is very sensitive to the magnitudes of variables. So that's why we take the training set and deselect the response variable and scale the result, and then make it a data frame, call it train X. We'll do the same thing for text, for the test set. In our data set, in the Boston data set, I think all of the features are already numeric, so we don't need to convert to any other transformations. Just scaling is very important. And we have to scale the training set and the test set separately. Keep this in mind. Don't scale them first. Scale the data first and then do the split, because then the information in the test set will be there will be a leakage of information from the test set to the training set, because if you calculate the mean and standard deviation using all of the observations, including the test observations, then obviously the statistics will contain information about the test observations. So this is not good. I have to scale them separately. All right, now let's see how to fit the KNN regression model. So the syntax is very similar to the original KNN model in the class package. Specify the training X matrix, the test X matrix, and the Y vector for the training data set. So all of the k-nearest neighbor models do the same thing. They just store the training observation values. So that is the modeling part. No actual model will be built. We just store or memorize the observations in the training set. And of course, you also, and immediately it will do prediction for the test set. Right? You just need to specify how many neighbors you want to use to do the prediction. Let's start with 10 first. Let's use 10. And save the result in mod KNN. And then use mod KNN to do pull out the predicted value for the test set for the y-hat test. Then immediately we can use our root mean square error function to calculate root mean square and also calculate the R square on the test set. So it's 85.37%. So this is the first KNN regression model we built with k equals 10 without tuning yet, right? So naturally we can tune it. So this time let's do it manually. I think probably Carrot cannot do it. The Carrot package is not a very new package, so it might not be able to tune all of the machine learning models. I guess this KN reg function is not included. So let's do it by ourselves. We can just consider some k values. Like for example, we consider values from 1 and then even numbers from 2 to 20. So totally there'll be 12. There'll be 12 different k values. And for each value, we can use the sapply function to do prediction. So before we do that, we actually create a function to fit the model with k neighbors, and also do prediction and calculate the root mean square error directly. So this whole thing will do everything. Take the training set and the test x set, text x and text y. Everything is provided in the function. And the k has a default value, which is 1, but it can be changed apparently. Okay. And then we can use the sapply function to apply this make kn predict function on different values of k. Okay, it's like an implicit loop. Right? And don't forget to provide other argument values because all of these are needed in the function, in the make kn predict function. So we can do the same thing for the training set and the test set. For the training set, pay attention. We are doing in-sample prediction and calculate the root mean square error for the training set. So that's why when we calculate root mean square error for the training set, the test x and test y are equal to the train x and the train y. Right? Don't be confused. That's because we want to still calculate root mean square error for the training set. Right? And for the test set, we use test x and test y. And then we can use the which function, which mean function to find the k value, the index of the k value, which has the smallest root mean square error, and save it here, which is the best k. And then we can use this if-else function to sort of figure out the fit status. So if k is smaller than best k, then overfitted. Otherwise, if it's equal, then it's the best fit. Otherwise, it's underfitted. Why? Because actually, the smaller the value of k, the more complex the model is. The complexity of the model is bigger, actually. For example, the extreme case is when k is equal to 1. So this is corresponding to the maximum complexity of the model. Okay. So that's why for K that is smaller than the best value, for example, from our, in the result, the best K value is 4. So for K values that are smaller than or smaller than 4, the model overfit, right? Because they are overly complex. Okay. And on the other hand, if K is greater than the best K, then they underfit. They are underfit. So this is all right. So this part just figure out how to create this data frame and then make it a table using the table function. Anyway, let's take a look at the result. Okay. It turns out that the best K is 4, and the training root mean square error is 3.33, and the test root mean square error is 4.78. Okay, and so this is the best model. And then we can use our functions to calculate the R square for the test set. So it's 85.9%. It's slightly better than the decision tree even, right? But it's still lower than the random forest model. So far, then let's compare the models we have talked about using the Boston data set. So first one is a linear model. And the R square on the test set is 78.4%. And then with the decision tree, and the optimal model yields the R square, which is 84.7%. And then random forest, 90.2%. And lastly, KNN model with K equals 4, have 85.9%. So obviously, all of the models are better than the linear model. Although we put all of the variables in the model, it's a full model.